Shafrin, and I'll be introducing the heat exchanger control experiment today. So as you can see, a heat exchanger is used to study the characteristics of the proportional integral, and proportional integrative controller on the temperature process control loop. The heat exchanger used in this experiment is a shell and tube heat exchanger with one shell and two tube passes. In the heat exchanger, the hot water is circulated in the tube side and the hot water returns to the hot water tank. The cold water is circulated in the shell side and the product is collected in the product tank. The purpose of this experiment is to control the flow rate of the hot water. So a control valve is used to do this. In the control valve, the opening percentage will be bigger if we want a higher flow rate, and vice versa, where the opening percentage will be smaller if we want a lesser flow rate. As you can see here, there will be inlet and outlet, and there will be a pressure difference which causes the flow rate to vary.
Hi, my name is Rashmi, and today I'm going to talk about the procedure of this experiment. So first of all, for the general setup procedure, we will have to ensure that all the valves are set according to what's written over here, and which valves are supposed to be open and closed. After that, we need to fill in the cold tank and the hot tank. And then after that, we can switch on the main power, and we can set the temperature for the hot water, which is at 65 degrees Celsius. Once you've done that, we can once the temperature has reached up to 65 degrees Celsius, we can switch on the hot water pump and the cold water pump. And after that, we can proceed the experiment. For the first part of the experiment, which is the controlling using the P proportional only heat exchanger control. And first of all, we can insert the value of the P, I and D. The P value is 20, the I value is 9,999 seconds, which is the maximum value, and the D value will be 0 seconds, which is the minimum. And after that, we can change the, we can include the set point, we can put in the set point which is at 45 degrees Celsius, and then we can switch on the recorder and turn the control loop into auto mode. And once the results, the measurement stabilizes, we can turn off the recorder and change back the control loop into manual. After that, the experiment can be repeated using different values of P, I and D. For the next part of the experiment is proportional and integral heat exchanger control. So for this experiment, we are using the same procedures as the previous one, but except that we are changing the value for the P, I and D values. The P value should be 100, the I value should be 120, and the D value should be 0. The reason why we are using D for 0 is because we are not using any derivative controller inside our experiment for this part. Repeat the experiment by manipulating the I value, which will be at 30 seconds to see the difference between the integral controller. And for the last part of the experiment is the PID controller, and it follows the same procedures as the previous one, except that for this part of the experiment we will be including the derivative value, which will be the derivative value first we set at 300 seconds, and then we repeat the same experiment, and to compare it we can change the derivative values to 60 seconds, but the proportional and integral value should be the same. And now I'll be talking about the flow of our experiment. So first of all, the hot water travels from the hot tank and the cold water travels from the cold tank, and this is the product tank where the cold water goes into it after it has been heated up to its set point. So the cold water flows from here and enters in the shell and tube heat exchanger. The cold water acts as the it enters at the shell side and the hot water enters at the tube side. And once the cold water has gone into the shaft side, it comes out through here and it goes through here into the product tank. And the product tank is left out to drain the water because we will be needing more water after that. And at the first side, there is a thermocouple and a transmitter that will actually send the readings of the controller of the temperature to the control system, and through that we can manipulate the temperature of the hot water and we can know what is the temperature. And same goes to the product of the once the cold water comes out from the shell and tube heat exchanger, we can know that the temperature of the product from this transmitter over here, which will be sent to the control panel for us to determine later on.
Hi, my name is Nur Hidayah and I will be presenting about result and discussion for this experiment. As we can see here, this is a graph response when we are using P controller. The graph, we can see that the set point of this experiment is 45 degrees Celsius. However, when we are using P controller, the response did not achieve the set point, which is only 30 degrees Celsius. So, the next objective is using PI controller. The top one is the response graph of using set 1, while the down one is the response graph of using set 2. Sorry. So, if we are using PI, we'll be having value of P and I, while D value will be 0. But the difference between set 1 and set 2 is set 1 have higher value of I compared to set 2. So as we can see here, the time taken for set 1 to reach the set point is longer than time taken for set 2 to reach the set point. And we can see also that in set 2, there is oscillatory response. So it is better to have lower value of I in this experiment since it will be having shorter time to reach the set point. So for next experiment, we'll be using PID controller. So when we are using PID controller, we will be having value of P, I and D, but for this experiment, we want to see which value of derivative is better. D value for set 1 is higher than set 2. So we can see here the time taken for PV to reach the set point of 45 degrees Celsius in set 1 is shorter than set 2. So for derivative, it is better to have D value, higher D value compared to lower D value. So comparing PID set 1 and also PI set 2, we can see that PI set 2 have longer time to reach the set point compared to PID set 1. So we can conclude from this experiment that it is better to use PID with higher value of D to achieve the set point in faster.
Hi, my name is Ikmal Hakim Zaman, and today I will explain about the conclusion for the heat exchanger experiment. Come here. So basically, I will recap about the objective. For this experiment objective, basically we will study the characteristic of P controller. Next, we will study the characteristic for PI, and lastly, for the PID. For your information, for P controller basically, it will reduce the offset, but we won't reach the set point at all. Next, for the PI, basically for PI, it will eliminate the offset. So, there will be no offset, but it will produce oscillatory. And lastly, for the PID. And for PID, basically, it will eliminate the offset, but it will reduce the oscillatory. So, as a result, basically, PID is the best controller compared to P and PI. Because we can get an accurate result, we can reach the set point faster. And for your information, what happens if I increase the integral time, which is the I value? Once we increase the I value, basically, the response time will be lower. so we'll make it faster. But for d value, which is the derivative time, once we increase the derivative time, the response time will become faster. Okay, so come here. So what is this? This is basically heat shell and tube heat exchanger. We have many type heat exchanger in this world, but today we will focus on heat exchanger, shell and tube. The application that we use in our daily life is, we say, refrigerator, the one that we use to store food, and next, air conditioning, the one that gives us cool air. So basically, that's all from me, and yeah, thank you.